So this is Lehman College's first semester of algebra, sometimes called abstract algebra or modern algebra. And what you should see on the screen is the textbook that we're using this semester. It's a Dover paperback by Alan Clark called Elements of Abstract Algebra. And it has two advantages. One, it's a very good book. And second, it's not expensive. So that's the book we're going to use, and what we're going to cover is the first four chapters: set theory, group theory, field theory, and what is called Galois theory. So I believe everyone is muted, but if you want to speak, you can unmute yourself and ask a question at any time. Okay. So on the Blackboard website for the class, there is a lot of information. Obviously, if you're here, you found the Zoom login, so you were able to log in. There is the grading system. Basically, we have homework, two midterm exams, and a final exam. There's homework due essentially every week. You will do your homework by writing it out, and then you need a way to scan it. And every printer these days allows you to scan and convert the scan to a PDF file. And then you go to Blackboard and you will upload the homework PDF file to the appropriate place in the assignment section on Blackboard. And the exams will work the same way. When there's an exam, at 9 o'clock, I will email you and post the exam. And by 11, when you have to have finished, really 10:40, but a little extra time because of all the computer business, you scan your homework pages and upload the PDF file again to Blackboard. Other office hours. So I have two kinds of office hours. I will establish some regular office hours where, let's say, every Monday, Wednesday, Friday at a certain time, I'll be on Zoom if you want to ask questions. But I understand that people's schedules are complicated, and I can also arrange appointments with you individually. It's always on Zoom. But if you have some questions, just contact me by email and we'll set up a time and you'll be able to log in and ask some questions then. Okay. Any questions at all before we start? So there's a difference between the kind of algebra you learn in high school and what is called algebra in mathematics. Part of it is built into the name of the subject, which is abstract algebra. There are a certain amount of abstract concepts that you have to learn. And it takes some getting used to. So this is a class that should take a lot of work on your part, not because we cover a lot of material, but because for many people, this is the first time they deal with abstract mathematics. Calculus is not very abstract. It's very concrete, very computational. But in algebra, we learn about certain things like groups and rings and fields, and we have to prove properties about them and get to know them. So in the beginning, often it takes a little bit of getting used to, and the more time you can spend reading and thinking and working problems, the better you will be. Okay. So all of the lectures, all of the lessons will be recorded, and I will set up a site on YouTube where you can go back and and review the lecture if you want, or watch the lecture if you missed it the first time. So that's what happens. Also, at some point in every class, I take attendance. If you have to leave early, try not to leave before I've taken the attendance. I don't do it right away because there are always people who enter late also. And I have to record attendance with the state of the college by the end of the second week. So it's really important that that I get you logged in at some point. All right. Any questions before we start? So we're going to start with what is often thought to be the simplest or the basic problem in algebra, which is solving equations. And I left a space between solving and equations because the different kinds of equations to solve. In calculus, you solve, for example, differential equations. In algebra, maybe it's easier. We want to solve polynomial equations. So polynomials are things that look like 2x cubed plus 7x squared minus 10 equals 0, or 13x to the 25th plus 17x to the 19th minus 2x to the 8th minus 3x squared plus 7 equals 0. I like to write often my polynomial equations with all the non-zero terms on one side and equals 0 on the other. But obviously, if you had an equation like 3x to the 4th plus 2x equals 7x cubed minus 19, that's the same as 3x to the 4th minus 7x cubed plus 2x plus 19 equals 0, right? You can always move things from one side of an equation to the other. Okay. So we want to solve polynomial equations. And one way we classify polynomial equations is by the degree. So the degree of a polynomial, let's say I'm using x as my variable, is the highest power of x that occurs with a non-zero coefficient. So for example, this polynomial has degree 3. This polynomial has degree 25. These polynomials have degree 4, and so on. And in a certain sense, it's not precise, the higher the degree, the more complicated the polynomial. So let's try to solve polynomials. So let's say degree 1. So polynomial of degree 1 is ax plus b equals 0. And it's of degree 1. That means this coefficient a is not 0. So if you divide by a, you get x plus b over a equals 0. Or x equals minus b over a. That's the solution. So solving a polynomial of degree 1 isn't so hard. What about degree 2? That means the highest power of x is x squared. Degree 1 equations are called linear. Degree 2 equations are called quadratic. And in high school, you're supposed to learn a formula for solving any quadratic equation. And you really should have memorized it, but we can just work it out. So we say that a polynomial is monic if the coefficient of the highest degree term is 1. So in this quadratic, the highest degree term is x squared. The coefficient is a. Again, a is not 0. That's if it has degree 2. How do I get a monic polynomial from this? I just divide by a. So if I divide by a, I get x squared plus b over ax plus c over a equals 0. And any solution of this equation is a solution of this equation, and conversely. So I can try to solve this monic polynomial. And of course, if this b over a term weren't there for 0, this would just be x squared plus c over a equals 0. So you would just take the square root of minus c over a. So with that in mind, you could try to do what we call completing the square. So step 1 was to make the polynomial monic by dividing by the leading coefficient. The next step is complete the square. I have x squared plus b over ax plus c over a equals 0. I'd like to add something to this to make this a perfect square. And what I can add is b squared over 4a squared. Of course, what I add to one side of an equation, I have to add to the other side of the equation. So this equation and this equation are equivalent. But the whole point of adding this quantity is that this is x plus b over 2a squared equals b squared. I said I like to have everything on the left, so minus b squared over 4a squared plus c over a equals 0. And let me introduce a new variable. Let z be equal to x plus b over 2a. So this equation is z squared minus this expression. If I put it over a common denominator, I get b squared minus 4ac over 4a squared equals 0. So all we've been doing here is high school algebra, just learning how to solve a quadratic equation. So what we've done is the following. We started with the equation ax squared plus bx plus c equals 0. And by doing some little high school algebra tricks, we got with the new variable z equal x plus b over 2a, the equation z squared equals b squared minus 4ac over 4a squared. So if you take the square root, z is equal to plus or minus the square root of b squared minus 4ac over 4a squared. 4a squared is a perfect square. This is 1 over 2a times the square root of b squared minus 4ac. So we started with a general quadratic equation. we did a little algebraic manipulations. We divided by the leading coefficient a, and then we completed the square, and we got this equivalent equation, which we could solve just by taking a square root. And what is z? Z is x plus b over a. So z, which is x plus, b over 2a, is equal to plus or minus 1 over 2a times the square root of b squared minus 4ac. So this is equal to, so x is equal to minus b over 2a plus or minus square root of b squared minus 4ac over 2a, which is minus b plus or minus the square root of b squared minus 4ac over 2a. So that's the quadratic formula for solving any quadratic equation. If you have this quadratic equation, ax squared plus bx plus c equals 0, that's the solution. So again, you're supposed to know this formula. If you've forgotten it, learn it, memorize it. I mean, this is really one of the things that everybody should know, no matter what your subject is. But knowing how to solve a quadratic equation is fundamental. And there's several important things to know about this. One is it's explicit, and the solution involves the coefficients of the quadratic equation you started with, a, b, and c, plus some numbers and addition, subtraction, multiplication, division, and the square root. So you had to take a square root to solve a quadratic equation. Okay. And now notice this makes sense even if b squared minus 4ac is less than 0. And you can say, well, but you can't take the square root of a negative number. But of course you can. So you must be able to use complex numbers. Okay? And I have to assume by the time you've gotten to a 300 level math class that you're familiar with the complex numbers, x plus iy. So, and we're going to use complex numbers in this course all the time. So I might email out some review of complex numbers if you haven't seen it for a while. It's actually in your calculus book from Math 175, 176, but I will email out the kind of review of complex numbers just to make sure that everybody is able to use them. Okay. Any questions about this? You can either unmute yourself or put it in the chat if there's a question. Okay. Well, that's a quadratic equation of degree 2. So next comes degree 3 polynomials, which are called cubic. And ax cubed plus bx squared plus cx plus d equals 0 is the general equation of a cubic equation. Again, cubic means the degree of the leading term is non-zero, right? So there really is an x cubed term that occurs. And to simplify this a little bit, the first step might be to make it monic. By dividing by a. So you get x cubed plus b over a x squared plus c over ax plus d over a equals 0. So any solution of this first equation is a solution of the second. And this one has the advantage that it is monic. Now, there's another simplification which you can do, which is actually to eliminate the x squared term, the quadratic term. You'll remember when we solved the quadratic equation, the first step was to make it monic by dividing by a, and then we completed the square, which removed this linear term, the term of degree 1 less than the degree. And we made a substitution, z equal x plus b over 2a. And when we did that, we got an equivalent quadratic equation which had no linear term, just the quadratic term and a constant term. It actually looked like this. Z squared, degree 2, constant, which is degree 0, with no linear term. And I want to do the same thing with my cubic. I want to eliminate the term which has 1 degree less than the numerator. And I can do this by substituting z equal, let's make this x minus b over 3a. And sorry, let me say it differently. What I'm going to do is let x be equal to z minus b over 3a. Now, when we substitute that, what do we get? Well, we plug this into the equation. The first term is x cubed. What is x cubed? X cubed is z minus b over 3a cubed. Now, how do you cube something? Let me just make a little note over here. If you have u plus v to the first power, that's just u plus v. If you have v plus v to the second power, that's u squared plus 2uv plus v squared. If you have u plus v to the third power, that's u cubed plus 3u squared v plus 3uv squared plus v cubed. These are just the 3 simplest cases of what's called the binomial theorem. And this formula for cubing something, you have to know. If it were u minus v cubed, it would be u cubed minus 3u squared v plus 3u v squared minus v cubed. I mean, it's the same thing with v replaced by minus v. So what do we get when we cubed z minus b over 3a? We get z cubed minus 3z squared b over 3a plus 3z b over 3a squared minus b over 3a cubed. So this is z cubed minus b over a, the 3's cancel, z squared, plus b squared over 3a, this is 9a squared. When you square it, 3 over that is 3a squared times z minus b cubed over 27a cubed. So if I was lucky enough to do my algebra correctly, this is what I got. So if I take x cubed plus b over ax squared plus c over ax plus d over a, and I substitute x equals z minus b over 3a, I get first, when I plug in z minus b over 3a for x, I get this. Z cubed minus b over a z squared plus b squared over 3a squared z minus b cubed over 27a cubed plus b over a times x squared. X squared, that's z minus b over 3a squared plus c over ax, which is b minus z minus b over 3a, plus d over a. Let me expand all this. So I get z cubed minus ba over z squared plus b squared over 3a squared z minus b cubed over 27a cubed. This is z squared minus 2b over 3a z plus b squared over 9a squared. That's just a quadratic, just squaring something. So I get a plus b over a squared minus 2b squared over 3a squared z plus b cubed over 9a squared times a, 9a cubed, and other stuff, all this stuff. But the important thing for us to notice is that this term and this term cancel. So in the end, this is z cubed. There's no z squared term. There's something times z minus some plus or minus some number I'll call q. That's what our equation is. So by making this substitution, x equals z minus b over 3a, I get a reduced cubic equation. This is a cubic polynomial, which is first of all monic. The coefficient of the cubic term is 1, and no quadratic term. So what this tells us is if I want to solve a cubic equation, the first thing I can do, if I like, is I can reduce it to a reduced cubic of this form. And if I can solve a cubic of this special form, I'm done. So Actually, just to be in sync with the text and use the same notation, I'm just going to call this Q and this R. So every cubic polynomial is equivalent to a cubic of the form x cubed plus qx minus r equals 0. I can assume that it's monic and there's no quadratic term. By the way, everything that I'm doing right now is in the introduction to the textbook. So this is certainly something that you should be reading. It's just a few pages, and it begins with this discussion of how you solve a cubic polynomial. Okay. Now, how do you solve a cubic? For a long time, this was a mystery, and it was finally solved in the Renaissance around the 18th century by a group of Italian mathematicians. And one way to solve it is to use the following trick. Suppose we let x equal u plus v. So we're going to substitute in our equation x equals u plus v. You might say, well, that's weird because we're replacing one unknown variable with two. Oh, someone asked why I took x equals z minus b over 3a. Why I did this. And the reason is that if I make this substitution, I eliminate the quadratic term in the equation. The point was to simplify the equation by getting rid of the quadratic term, and this substitution will work. Why did someone think of this? Well, somebody was clever and thought of it. It's always good to be clever, but if you're not, it's good if someone else is and you can learn from what they did. So someone was clever 300 or 400 years ago, and we learned from what they did. And someone else was clever and said, okay, let x equal u plus v. So if we plug this into this equation, we get u plus v cubed plus q times u plus v minus r equals 0. Let's expand this. U plus v cubed is u cubed plus 3u squared v plus 3uv squared plus v cubed plus q times u plus v minus r equals 0. Let's see, let's look at these first terms. I have a u cubed plus v cubed, and then I have these two terms. I can factor out a 3uv, and I get u plus v plus q times u plus v minus r equals 0. Now here I have a u plus v and a u plus v, so I can write this as u cubed plus 3 plus v cubed plus 3uv plus q times u plus v minus r equals 0. Now, suppose I choose V such that 3uv plus q is 0. In other words, V is minus q over 3u. Well, in that case, this term disappears, and what do I get? Now, if you're following in the introduction to the book, you'll notice that the discussion in the text is very concise, and I'm filling in a lot of steps. So in particular right here. So we have the equation u cubed plus v cubed minus r equals 0, where v is minus q over 3u. So that's u cubed plus v cubed, that's minus q cubed over 27u cubed minus r equals 0. If I multiply through by u cubed, I get u to the 6th minus q cubed over 27 minus r u cubed equals 0, or just to put this in the usual order, u to the 6th minus r u cubed minus q cubed over 27 equals 0. So you might say, well, you're worse off than when you started, because you started with a cubic equation in one variable, an equation of degree 3, and this is an equation of degree 6. But then if you stare at it for a moment, you'll see it is degree 6, but it only involves u to the 6th u cubed as powers of u. So this is really u to the 6th is u cubed squared minus ru cubed minus q cubed over 27 equals 0. This is really just a quadratic equation in u cubed. So we can solve for u cubed. U cubed, this is just a quadratic formula. Minus b, that's r, plus or minus the square root of b squared minus 4 ac, well, a is 1 and c is minus, q makes this plus, u cubed over 27 over 2. So this is r over 2 plus or minus 1/2 square root of r squared plus 4q cubed over 27. Let's see. B squared no, sorry. So minus b minus b is r plus or minus the square root of b squared minus 4ac over this over 2. Yeah, that's right. So u cubed is equal to r over 2 plus or minus. Now, when I have r squared plus 4q squared over 27, I can write r squared as 4r squared over 4, factor out the 4 and take the square root. That brings a 2 outside. So u cubed is r over 2 plus or minus the square root of r squared over 4 plus q cubed over 27. So if you are following in the text, this is equation 5 on page Roman numeral 10. Now, so that's u cubed, so we can find u. U is just the cube root. But let's recall something. Every non-zero number has 2 square roots. The square root of 25 is equal to 5 or minus 5. Square root of minus 25 is equal to 5i or minus 5i, the complex numbers. Square root of 1 is 1 or minus 1. Similarly, every non-zero number has 3 cube roots. What are the cube roots of 1? Well, 1, or if I write this as a complex number, minus 1/2 plus root 3 over 2i, or minus 1/2 minus root 3 over 2i. And you can check by cubing. So for example, minus 1/2 plus root 3 over 2i, when you cube it, it's minus 1/2 cubed plus 3 times minus 1/2 squared times root 3 over 2i plus 3 times minus 1/2 times root 3 over 2i squared plus root 3 over 2i cubed. Right? This is just the formula for cubing something. This is minus 1/8. This is 3 times 1/4 times root 3 over 2i. So that's 3 root 3 over 8i. This is minus 3/2. When I square this, I get 3/4 times I squared times minus 3/4. And when I cube this, I get 3 root 3 over 8 times minus I. What is this? This is plus 3 root 3 over 8i. This is minus 3 root 3 over 8i. Those cancel. This is 9/8, so I get minus 1/8 plus 9/8 equals 1. So if you've never done this calculation, you should do it. And you see directly that this number is the cube root of 1. And similarly for this number. In fact, if you remember, or if you will learn, you have to learn sooner or later. In the xy plane, if you take the circle, x squared plus y squared equals 1, any point x plus yi, the complex number, is just the point in the plane with coordinates x, y. So this is the point, the complex number, minus a half plus root 3 over 2i. This is minus a half minus root 3 over 2i. This is 1. And these three numbers are the vertices of an equilateral triangle. And these are the three complex cube roots of 1. So if you're not familiar with it, I guess, well, now you are. It's good. So when we're solving the cubic equation, z cubed, let's see, how did I write it in reduced form? Sorry, x cubed plus qx minus r equals 0. We substituted x equals u plus v, where v is minus q over 3 times u. So once you know u, you know v, and when you know u and v, you know x. And we got the cubic equation, u cubed equals r over 2 plus or minus the square root of r squared over 4 plus q cubed over 27. So u is the cube root of this number. And there are 3 cube roots. Remember, what are the cube roots? We have minus a half plus root 3 over 2i. Let me call that omega. Omega squared is, in fact, minus a half minus root 3 over 2i. Omega cubed, which is omega 0, is 1. So if you take 1 cube root, u is just omega to some I, or some j, I should call it, maybe 0, 1, or 2. I just take the cube root of this complex number. And now we've solved, in principle at least, the cubic equation. Okay. Well, the Babylonians 3,000 years ago knew how to solve a quadratic equation. At least they had an algorithm to do it. They didn't have a proof. But the cubic equation took 2,000 years to discover. So, and notice, to solve the equation, you need complex numbers, of course, and you need to be able to take cube roots and square roots. U cubed involves square root, and then you take the cube root. So let's recall, you can solve a quadratic equation using square roots. Can solve a cubic equation using square roots and cube roots. Well, The next thing to solve clearly is degree 4 polynomials. So ax to the fourth plus bx cubed plus cx squared plus dx plus e equals 0. Such a polynomial is called quartic. So linear is first degree, quadratic is second degree, cubic is third degree, quartic is fourth degree. And after that, you might try to solve a degree 5 polynomial, which is called a quintic. So we can, in fact, solve quartic polynomials using square, cube, and fourth roots. So just the way we could find a formula for solving the cubic polynomial, which involves square roots and cube roots, for a fourth degree polynomial, you can solve it using square, cube, and fourth roots. This was also discovered in the Renaissance in Italy in the 18th century, early 18th century. And this was really very important. But problem, is there a formula to solve a quintic or degree 5 polynomial? And no matter how hard people tried from the 17th, 18th centuries onwards, they couldn't do it. They just, I mean, they didn't know whether they weren't smart enough or what was going on, but they could figure out a formula for a fourth degree polynomial, but no one did for a fifth degree polynomial. And finally, late in the 19th century, not late, in the middle of the 19th century, a solution was found. And the answer is no. There's no formula to solve a polynomial of degree 5 that just involves taking square roots, cube roots, fourth roots, fifth roots, any roots that you like. And in some sense, the goal of this class is to prove this fact, that there's a formula for cubics and quartics, but no formula for quintics. Let me take a break for 1 second just to check the attendance. So I will call off your names, and if you don't hear your name at the end, let me know, because this is just in the order they appear on the participant list. So I have Abdul Debray, Aldo, excuse me if I mispronounce your names or when I mispronounce your name. Aldo Plumage, Amal Miu Bozuni, Ariani Espinal, there is a, let's see, Bubakar, that's Tapsobi, I think.
I'm here.
Okay, thank you. Ryan Alberto. Daniel Santiago.
Here.
No, I'm just reading off the list. If you don't hear your name at the end, let me know. Dorabel Duran. Edward Hernandez. And Edwin Hernandez, both. Okay, excellent. Estras Forch.
Here.
Yep, gotcha. Sturgis. There you are. Hassani Sidibi.
I'm here.
Yep, gotcha, thank you. Hilda Costa Acevedo. I have you. Ibrahim Diallo. Janelli. Is that Sedano Aquino? I assume so. Jessica Campos.
Here.
Yeah, thank you. Jonathan Campos.
Here.
Yep. Jose Keynes. Yep, got you here. Catherine Cruz. Leonie Rodriguez. Yang Sar.
Here.
Yeah. Lenny Gonzalez.
Is it Metalid Gonzalez?
So just 1 second. Jose Keynes, Catherine Cruz, Leonie Rodriguez. Yeah. Sar Medalit Gonzalez.
Here.
Good, thank you, got you. Numa Derame.
Here.
Yeah, no, that's fine, got you. Nicola Clark. Nicola.
Here.
Yeah.
Nicola Clark here.
Yeah, yeah. Somehow you're here twice.
Thank you.
Soto, Randa Soto, here you are.
Here.
Yep. Richard Benitez. Shelby Wright. Tamina Shalduri. Travis Headley. Vanessa Yu. Let's see. Angelo Alba. She was here. Tanvir Ahmed. Yes, no. Zanaya Haynes. No. Nasser.
Excuse me, is Wilayat Nasser?
I believe I got you. Just 1 second. Oh, yeah. Yeah, I have you here.
Okay.
So who I don't have is Tanvir. So if you hear your name right now, let me know. Tanvir Haynes. Sidby Wagan. Ilogu. Okay, good. All right, so So everything I just did is in the introduction to this volume. And so what you should do is read for Wednesday the introduction to the textbook. And let me just note, it's actually hard to understand. And one reason why it's hard to understand is he's really giving you a hint of things that are going to be developed in the course of the semester. And the reason to read the introduction now is, first, it's the introduction. It's not bad. And second, if you go back at the end of the semester and reread the introduction, then you will understand a lot of what you had not understood previously. Now, one of the things that is discussed in the introduction has to do with the quartic or degree 4 polynomial. And in general, a polynomial of degree 4, he writes it like this: x to the 4th minus px cubed plus qx squared minus rx plus s equals 0. The plus and minus signs don't really matter very much, but they're not bad. So in general, a polynomial has as many solutions as its degree. So this should have 4 solutions. And let's say they're alpha 1, alpha 2, alpha 3, and alpha 4. And they're going to be different ways to, well, actually, I shouldn't say quite like this. That they're going to be 4 solutions, and you could take some combination of them, like remember, I squared is minus 1, is that complex number. So you get some expressions like this, and you can interchange the alpha 1, alpha 2, alpha 3, and alpha 4. What I mean by interchanging them is the following. You could have alpha 1, alpha 2, but let's just say we have 3 numbers. And I could have them in this order: alpha 1, alpha 2, alpha 3. Or I could fix alpha 1 and interchange alpha 3 and alpha 2. Or I could fix alpha 2 and interchange alpha 1 and alpha 3. Or I could write them in the order, instead of 1, 2, 3, alpha 2, alpha 3, alpha 1. Or maybe alpha 2, alpha 1, alpha 3. Or maybe I don't change them at all. Let's see. So I can arrange these in different ways. Actually, I can even forget the alphas. I can just think of the numbers 1, 2, 3. I can write them in order. I can write them in different orders, like 1, 2, 3. 1, 3, 2. 3, 2, 1. let's see, 1, 2, 3. Here, I fix 1, I interchange 2 and 3. Here I fix 2, and I interchange 1 and 3. Here, I fix 3, and I interchange 1 and 2. Or I can go, instead of 1, 2, 3, 1, 3, 2. Or let's see, I'm missing one. There should be 6 different ways to put these numbers in order. So I have, oh, wait, this one I've duplicated. I can have 1, 2, 3 or 1, 3, 2. I can have, this is an easier way to do it. If I put 2 first, I can have 2, 1, 3 or 2, 3, 1. If I put 3 first, I can have 3, 1, 2 or 3, 2, 1. And these are all the possible arrangements of 1, 2, and 3. These are called permutations of the numbers 1, 2, 3, and there's 6 of them. There's 6 ways to take the numbers 1, 2, 3 and write them in different orders. And it's not obvious at all, and this was one of the great discoveries that created abstract algebra, that somehow studying permutations of this sort is connected to solving polynomial equations. So when you have permutations of a set of objects, they form what's called a group. I haven't defined it. I'll talk about that next week. They form a group. And in order to understand polynomials, it turns out we have to develop what is called group theory. And after some introductory lectures, Wednesday of this week and next Monday, when we start to go through chapter 1, as soon as we're done with that, we will spend a lot of time studying groups. So that's where we are. So this is all, I think, all I'm going to do today. This is, there are really 2 points to the lecture today. The first is that one of the historical origins of algebra is trying to solve polynomials. And linear equations and quadratic equations were known for thousands of years. Cubic equations were much harder. No one found a solution of the general cubic until the 17th, early 18th century. And at the same time, or shortly thereafter, also, they found a solution to a 4th degree or quartic polynomial. 5th degree polynomials were a problem, and then it was one of the great discoveries in mathematics is that there is no way to solve the general quintic or 5th degree polynomial. Some easy ones you can solve, but in general, there's no formula. And that was discovered by 2 mathematicians, a Norwegian named Abel and a French guy named Galois. They both had the misfortune of dying when they were very young. Abel died when he was in his 20s. Galois died in a duel. They liked duels in those days. He died in a duel when he was around 21 years old. But he did leave this mathematical work for which he is really famous. And what is called Galois theory is what we will study in chapter 4 of this of the textbook in the course. Okay. So for Wednesday, the assignment is just to start to read the book, to read the introduction, and the more you read and the more ahead you read, the better, because it's always good to have seen things in advance before the lectures. And then and every Monday, basically, unless there's an exam, every Monday there will be a homework assignment due, some problems to do. and I will email them out to you before Wednesday's class. But the homework will be is due every Monday. And I will always go over homework problems in the lectures, not all of them necessarily, but certainly any ones that you want to ask about. Okay. Any questions about anything substantive or procedural? Yeah, go ahead.
I just wanted to confirm that you will be posting this video on YouTube.
Yes, but I'm still trying to set up the right video channel and playlist. So as soon as it is posted, which will hopefully be sometime today, I will email out to everyone in the class the link to the recording.
Okay, thanks.